this is lecture 25. So a quick summary of what we have been doing throughout this course. So we started off with the need of a nonlinear element in order to get in order to make a device which in order to make a net circuit which can give us power amplification. Then we saw that a certain type of nonlinearity is required. Not all nonlinearities will give us power amplifications, and based on our requirements, we zoomed into the fact that the device that of our choice required certain characteristics which had very high output impedance, very high transconductance, very high input impedance, right, and and very small reverse conductance, right, between port 2 to port 1. And then we saw that we could do that using a MOSFET. In particular, we used an NMOS, right? So and in order to, then we further extended the arguments and said that now that we have a MOSFET to make an amplifier, we would also want to ensure that the amplification factor or the factors that control the amplification, like GM, GDS, and so on, we would like them to be stable with respect to change in ambient conditions. In other words, we wanted those factors to be robust to any change in ambient conditions, especially temperature, especially voltage swings, and so on and so forth, right? And then we saw certain types of biasing. We saw that we required constant current biasing. For that, we had to devise current mirror based biasing, and so on and so forth. So however, there is one still niggling problem, and that is what we would like to see in this lecture. So now this is our humble common source amplifier, and by now we know how to bias this guy, so in various ways. So we will not bother about that for the time being, and we'll go back to our classical way of biasing the common source amplifier, right, with a voltage source. But we should always keep it at the back of our mind that there are multiple ways of biasing, right? So this is easy to draw, so I drew this. So this is VDD, this is RL, VGQ, VI, and we need V naught here. And we saw that the gain, that is V naught over Vi, in this case a small signal gain, was the GM of the transistor times RDS of the transistor parallel RL, right? And if we say that RDS is much higher than RL, like in case of an ideal transistor, RDS is infinity, right? This becomes approximately equal to minus GM1 times RL if RDS tends to infinity. Correct? Okay. So now, if we look at this for that, if we stare at this equation, what is it telling us? It is essentially telling us that the gain is proportional to two things. One is the transconductance of M1, and other is the load resistance RL, right? So now, or let me call this the drain resistance. Excuse me. Let me call this a drain resistance, RD, because by definition the load resistance is not a variable, right? So let's assume this is a drain resistance RD. Okay, so what does GM depend on? GM depends on the size of the device, GM depends on VGQ, the overdrive voltage, and so on. And what does RD depend on? RD is the biasing resistance on top. So if I have to increase, let's say I fix the value of GM, right? And if we have to increase the gain, what should we do? If GM is fixed, if GM1 is fixed, to increase gain, we need to increase RD. fine, this is okay, this is all right, we can do that. But do you think we can do it indefinitely? For example, if I want, if let's say I have a gain of 10, I want a gain of 20, I doubled RD. Then I want a gain of 40, I doubled it further. I want a gain of 80, I doubled it further, and I kept on going. If I keep on increasing RD, do you think this architecture will work, or there is something that can be problematic? Clearly, there will be something that will break, and I'm sure you have already identified it. What will break? The biasing condition of the transistor M1 will be a problem, right? So we all know that M1 should be in saturation, right? In saturation, what is the characteristics of a transistor in saturation? The characteristics of a transistor in saturation is that the current through the transistor IDS is not dependent on the drain voltage, right? Which means this is a current source. If it depends on the drain voltage, then it doesn't become a current source. So in a transistor in saturation, for a transistor in saturation, IDS is independent of the drain to source voltage, right? And what is the limit of saturation voltage? The limit of saturation voltage is the quiescent voltage at this node V naught Q should be greater than equal to VGQ minus threshold voltage. Now, if you fix VDD, VDD is fixed, and if you keep on increasing RT, what is happening to the quiescent voltage? The quiescent voltage at V naught is going down, lower and lower and lower, right? So if it goes lower and lower, ultimately it will hit this limit, and the transistor M1 will no longer be in saturation. If it's no longer in saturation, then the output resistance of the transistor drops dramatically, hence the gain will start to drop as well. So what is the solution to this? The solution to this, one of the solutions to this is to say that, hey, it looks like the only thing that we need to do is to ensure that the voltage at the drain of M1 should always be higher than VGQ minus threshold voltage. Now, what is the voltage for a fixed IDS? What is the voltage at the drain of M1? This is VDD minus IDS times RD. And if we have to keep this above certain limit of VGQ minus threshold voltage, while I will increase RD, what do we need to do? We need to keep increasing VDD as well, right? So what is the conclusion? The conclusion is to ensure M1 is in saturation even after increasing RD, we need to increase VDD. Right? So since and that is why in some of the problems that you have already done in this course, you would have seen that sometimes the choice of VDD is 5 volts, sometimes the choice of VDD is 7 volts, sometimes the choice of VDD is 10 volts. The different choices of VDDs are there so that we can ensure that the transistor in question remains in saturation. However, this is a problem, right? The problem can be expressed in two fronts. One is we seldom have a choice of VDD. In several technologies, or in almost every chipset that you will see, there is typically one battery that powers the entire system, and the battery is of some value, maybe 3.3 volt, maybe 5 volt, maybe 1.2 volt. There will be some battery which powers the entire system, and you will have to run everything along. You have to run the entire circuit by drawing current from that battery. So if that is a problem, I mean that will become a big problem, because now essentially what we are saying, we are saying that we cannot keep on indiscriminately increase the value of RD, because there will be a certain maximum value of RD beyond which I will not be able to keep the transistor in saturation. Now if that is the case, that limits the maximum amount of gain that I can get out of a configuration of a common source amplifier, right? So, which means that for a fixed VDD, for a fixed, therefore, for a fixed VDD, we cannot increase RD indefinitely, right? Since we will not be able to increase VDD, RD indefinitely, this limits the maximum possible gain from a common source amplifier. Okay, so now that raises a problem that, what should we do? Should we say that, okay, this is what it is, we cannot do anything, or should we explore further? As it turns out, we can do something, and whatever we can do is based on one critical observation, and the observation is as follows. So if we are trying to figure out what is the incremental output impedance at this node, right? What is the incremental output or out? What do we see? The incremental output impedance is the parallel combination of the impedance that we see looking up and the impedance looking down, right? What is the impedance looking up? This is RL. What is the impedance looking down? This is RDS, right? And since RL is less than RDS, in case of most devices, RL will be much less than RDS. This approximately becomes RL, since RL is generally much less than RDS, right? Or rather say, if RL is much less than RDS, which generally is the case. And why do we generally have RDS to be very high? Because the drain impedance, the impedance looking into the drain of a transistor is ideally infinite, right? So this is because, so RDS for a MOSFET in saturation tends to infinity, right? Ideally, this is ideally. So essentially what we are saying is, what we are essentially saying is, in place of this device RL, if we can put another transistor, right, whose drain terminal is connected to this node, right, whose drain terminal is connected to this node, then we are all set, right? So essentially what you are saying is, if we can replace RL with a transistor whose drain is connected to V0, right, then R out would be equal to RDS, let's say this is M1, RDS1 parallel some RDS2, where RDS2 is the output impedance of the second transistor. right? Then it is possible to do so. And why is it why this is a lucrative thing to explore? It is a lucrative thing to explore because at the end of the day, the RDS does not depend on the voltage across that between the drain and the source of the transistor, right? Right. So what we are essentially saying is, in this architecture, the gain is dependent on the quiescent drop across RD, right? Or yeah, so in this case okay, we are using RL, so let's use RL. The gain is dependent on the quiescent drop across RL, because moment we increase RL to get higher gain, then naturally the drop across RL increases. However, the quiescent drop across a transistor does not determine RDS, right? So this is possible, right? So note that the quiescent PDS does not affect RDS as long as PDS is greater than equal to VGS minus threshold voltage, right? So this is a big positive, right? So in essence, we will be able to decouple the gain from the quiescent conditions. If we can decouple the gain from the quiescent conditions, then it is probably possible to get higher gain with a limited power supply. Now, in order to get higher gain, we have no other option but to increase the power supply. However, now if we are able to use MOSFETs, right? If we are able to use MOSFETs in place of RL, then it is probably possible to decouple the biasing condition from the achievable gain, right? So let's see if that is possible. So what should we do? So let's sketch our common source amplifier once again. So what do we need to do? Here we have VDD. So here we need to put something. We need to put a transistor whose drain is connected to V0, right? So since we know that the transistor physically is symmetric device, geometrically there is no distinction between the drain and the source, right? So we can just put a device here, and let's assume something is biased here, right? So let's say this is biased with some voltage V2. It's an NMOS transistor, and let's assume this is in saturation, right? So do you think this is going to work? So before we get into the understanding of whether this is going to work or not, let's first identify which is a drain and which is a source terminal of this transistor, right? So what determines what is a source and which is the drain? The higher potential is always the drain in an NMOS transistor, right? So and also the quiescent current flows from higher potential to lower potential. The current will flow from top to bottom, which means naturally this terminal becomes the higher potential and this terminal becomes the lower potential. So this terminal becomes the drain and this terminal becomes the source, which means that the arrow, right, that determines the source goes at V0. So what is the consequence of this? What is the impedance of the transistor looking up into the source? What is the small signal impedance? So let me call this M2. So V2. So I am asking what is the this is M2, what is the small signal impedance Rn, looking up into the source. So you can replace this guy with its equivalent impedance. We have done that multiple times. And what impedance do we see? The impedance that we see is Rin is equal to 1 over Gm plus GDS, or Gm2 plus GDS2. So this is nowhere close to RDS, right? This is much lesser than RDS of the device. How could we have gotten RDS? We could have gotten RDS had this terminal been the drain terminal, but this is unfortunately not, and that's because the making of the NMOS transistor is such that the structure of the NMOS transistor is such that the lower potential is always source. But fortunately, we have another device which we haven't introduced till now, but it is time to introduce the device, and it is a device which is a complement, which complements the NMOS transistor, and that is called a PMOS transistor. So let's sketch the NMOS transistor cross section first. So let's say we are going back to the device cross section of a transistor once again. So let's say we are trying to make a PMOS transistor. So we have a p-type wafer, then we have a oxide layer. On top of that we have a polysilicon layer, you have a gate, you have, let's say we call this source, we call this drain, right? And if and let's say this is body n plus, e plus, and let's say the body and the source are connected for the time being. So if in this case, if VGS is greater than equal to threshold voltage, we have electrons in the channel, right? We have electrons in the channel. For the time being, let's also assume that the source and drain are connected, and there is a voltage between gate and the source, right? So if VGS is greater than threshold voltage, we have electrons in the channel, right? And then if we apply a drain to source voltage, right, the electrons tend to gravitate towards the drain, so the electrons move this way, and we get a current that flows from right to left, right? So this is I, right? And if we keep on increasing the drain to source voltage, we start having pinch off, and since we start having pinch off, we are no longer able to influence the channel charge from the drain, and hence we have high impedance from the drain terminal. So as it turns out, we also have a complementary device where all the dopings are of the opposite polarity, right? By that what I mean essentially is, so we have a device where the base is n-type and we have a doping here of p-type, and we have oxide on top, and we have metal layer on top of that, we have gate, then we have terminals connected here and here, and we have a body terminal, right? We have a body terminal, and body is also of n-type. Okay, so now let's see what's going to happen. So now what do you let's further assume, like in case of the NMOS transistor, the two terminals which we will be calling source and drain eventually are connected, and let's also assume that these two terminals are connected. just like in case of a NMOS transistor. By the way, this is called a PMOS transistor. This is called a p-MOSFET, just like this is called an NMOS FET. This is called a p-MOSFET. Okay, the reason this is called a p-MOSFET will be apparent just now. So, what do you think will be? What do you think will happen if we apply a voltage, a negative voltage between, or rather, if we apply a voltage such that that one of the terminals is at higher voltage than gate, right? So, by the way I have sketched, what do you think will happen? So, the electric field in the vertical electric field will, so this becomes a higher potential and this becomes a lower potential, right? Because the body of the PMOS becomes higher potential than the gate, the electric field will go from the body to the gate, right? So, the electric field will go this way. Since the electric field will go in this way, right, all the holes, let me use a different color, all the holes which are available here these are holes H plus will, all the holes will tend to accumulate under the channel, right? So, just like in case of the NMOS transistor, the electric field was going from top to bottom. Since the electric field was going from top to bottom, right, all the holes were getting pushed out and the electrons were getting attracted in the channel. The exact opposite is going to happen in this case. If we have an electric field whose direction is reversed, all the holes will get attracted to the channel and the electrons will get repelled, right? The electrons will get repelled from the channel. So, eventually what will end up happening is we will be having a channel of holes, right? A channel of holes that connects these two terminals. So in other words, in this case, if VSG, right? So which, I mean, we can talk about which is source, which is drain later on, but everything is connected right now. If VSG is greater than equal to certain threshold voltage, let me call this VTP, right? We have holes in the channel, right? And just like in case of an NMOSFET, what's going to happen if we let's say add a potential between one of these two terminals, right? Note that this is a higher terminal. We are making this guy as a higher terminal and this guy as a lower terminal, which means the electric field will go in this direction, which means the holes will move in this direction, which means the current will also move in that direction, right? The current will also move in this direction, right? So IDS will be moving in this direction. And what is the definition of drain and source? The definition of drain and source is source is essentially that terminal from which all the carriers are originating. In this case, the carriers are originating from the left terminal and moving towards the right. So this becomes the source terminal, right? So this becomes the source terminal and this becomes the drain terminal. and if we keep on increasing the VSD, right? In other words, if we, for a fixed source voltage, if we reduce the drain voltage, or for a fixed drain voltage, if we keep on increasing the source voltage, right, what's going to happen? You are going to have we are going to have a pinch off. Where? Which side are you going to have a pinch off? Clearly, again, towards the drain side, right? So essentially what's going to happen is we are going to have a pinch off towards the drain side. Because why? Because note that the channel is, in this case, is formed as long as the difference between the gate and the channel is negative, right? Negative beyond some value, right? So the gate has to be at a lower potential than the channel by a threshold voltage. Then only we'll have holes in the channel. Now, if the drain voltage is if the gate voltage is not sufficiently lower, than the channel voltage, right, you are not going to have inversion. The transistor will be in cutoff region, right? The same thing happened in case of an NMOS transistor. So what we are doing is trying to draw an analogy between an NMOS and a PMOS transistor. Okay, so the only other thing that we need to address is, it looks like in case of a PMOS transistor, the body needs to be of N type, whereas in case of in case of a PMOS transistor, the body needs to be of N type. However, in case of an NMOS transistor, the body needs to be of P type. So does that mean that we cannot make everything on a single P substrate? That would be a really problematic situation. As it turns out, no, we can do that. So for that, we just need to ensure that the PMOS has a separate well. So the PMOS is normally guarded off with a separate well of N type, and that local well becomes its own well in which it can reside in. Okay, so this is as far as the very rudimentary introduction to the device of PMOS is concerned. But more importantly, what we are interested in is the working of the PMOS transistor, right? And that is what we are going to see next.